Good. Hello, Peer 9 and people at home. We are computing some limits. Limits are hard because we are talking about infinitely small things, and we don't have a lot of experience with that. And so, if you would like proof that this is really hard, we will note that 85% of the people in this room, and you're all very smart people, did this basically totally wrong. These things are not obvious. We want to take the limit as x approaches 1 of x cubed minus 1 over x minus 1. Okay, so let's just imagine we're seeing this problem for the first time ever right now. What kinds of observations can we make? Well, as we discussed yesterday, we are interested in what this function is doing near x equals 1. What this function is doing at x equals 1 is not part of our concern. And if we want to talk about that just for a second, we will notice that this function is simply undefined at x equals 1, right? Because you cannot plug in 1. If you plug in 1, you get 0 on the top and 0 on the bottom, and you cannot divide by 0, and so 0 over 0 does not exist. But we are not asking what's happening at 1, we're asking what's happening near 1. So what is happening near 1? Well, let's just casually try to plug 1 into the top. If you plug in 1, what do you get, roughly speaking, in the numerator? 0. And what do you get in the denominator, roughly speaking? 0. Okay, so therefore this limit is a situation in which the top is approximately 0 and the bottom is approximately 0. In other words, we are in a situation in which we're dividing a very, very tiny thing divided by another very, very tiny thing. Okay, what happens when you divide two very, very tiny things?
You get a number.
Something happens. But, and Valentina's shrugging suggestively, as if to say, not that kind of suggestive, as if to say, I don't know what happens when we divide something tiny by something tiny. We'll have to edit this video. There is even a name for this. We call this an indeterminate form, 0 over 0. And I think just to distinguish between actual 0 over 0 and like approximately 0 over approximately 0, I call this a 0 over 0 situation. It's a situation in which both the numerator and the denominator are very, very tiny. And the conclusion is it's really hard to draw any conclusion from limits when they're in this form. Okay, and I can give some quick examples that kind of demonstrate this. Suppose I am taking the limit as x approaches 0 plus, you can maybe jot this on the back of your worksheet or something, of x squared over x. Okay, well, what is happening to x squared when x is very, very close to 0?
It's getting closer to 0.
It's very, hold on, it's very close to 0, and this denominator is also very close to 0. So is this a 0 over 0 situation?
Yeah.
Yes, it absolutely is. But, because I am only asking about what's happening near 0, not what's happening at 0, it becomes perfectly legitimate to just do a simple algebra cancellation. X squared over x just is x, as long as x is not 0. And therefore, the answer to this limit is revealed. What is the answer?
0.
0. It's getting very, very close to 0. Okay, but suppose I give you a slightly different limit, like x over x squared. Is this also a 0 over 0 situation?
Yeah.
It is, right? The numerator is getting really, really close to 0. The denominator is getting really, really close to 0. Yet, by a simple algebra simplification, what do we learn?
It's infinity.
X over x squared just is algebraically 1 over x, as long as x is not 0, which it isn't. And so what happens to 1 over x as x approaches 0 plus?
It gets really big.
It gets really big, yeah. 1 over something really tiny, positive is infinity. So already we are seeing that 0 over 0 situations are not to be trusted. They might turn out to be 0. They might turn out to be infinity. They might turn out to be, wait, Oscar, I got this. They might turn out to be 1, which is what a lot of you are assuming would always happen, but which is now, I think, been shown to be incorrect. And in fact, could be anything. If you give me a number, what was your number, Oscar?
74.
74. Well, suppose I have 74x over x. Is this a 0 over 0 situation?
Yes.
It is, because both the numerator and denominator are getting really, really close to 0. But of course, by canceling the x's, this limit is just the limit of 74, which is just 74. So the answer could turn out to be 74. It could even be negative, because suppose the top is x and the bottom is negative 3x, for example. Is this a 0 over 0 situation? Yeah, it is. The numerator is going to 0, the denominator is going to 0, but upon doing an algebraic cancellation, we find that this is negative 1/3. So the answer is just negative 1/3. Okay, just the point of this conversation is that if you have a 0 over 0 situation, you simply don't know what the answer is yet. You cannot conclude anything based on the limit being in this form, which is why we call it an indeterminate form. You can't determine it. Alright, so what do we do when faced with an indeterminate form? Like something. The answer is we have to do something else besides just noticing that it's like tiny over tiny. Okay, what is the something else? About like a third or half or maybe more of the tables figure this out. What is the something else? Yeah, you can factor. There's a couple ways of talking about this. One way is like, this is actually just a rational function, right? So like you are masters, or once were masters of graphing rational functions back in pre-calc C. This is just a cubic over a linear. What's one of the first things you might do to understand this rational function? You know, you would just factor it, or do whatever, right? Search for roots, like do polynomial division, all those things. In this particular case, it's pretty easy to factor because x cubed minus 1 is like a known thing. It's like a difference of cubes. So this is x minus 1 over x squared plus x plus 1. And, all right, when you write it like this, now we notice that, again, since I'm interested in what's happening near 1, not what's happening at 1, it's perfectly legitimate to just cancel these. And we even did stuff like this back in the graphing rational functions unit, right? If there was a factor in the numerator denominator, we canceled it because it doesn't change the overall function except for the fact that x can't be 1. Okay, so this whole thing just turns into like x squared plus x plus 1, and therefore the answer is 3. Yeah. And okay, so in this case, the answer turned out to be 3. I'm gonna just dwell on this problem for like another minute or two because I think it makes what's going on a little bit more explicit. But like, this is really just a quadratic, right? This x squared plus x plus 1. So let's get a graph of this quadratic going. If we complete the square, then this is like x squared plus x, like plus a fourth, I guess is what I want. Plus 3/4. You guys following this?
Yep.
So really this is like x squared plus a half, x plus a half squared plus 3/4. Okay, so now that I know that, if I set out to graph the function x cubed minus x cubed minus 1 over x minus 1, what I know is that this is equal to just x plus a half squared plus 3/4. Except that x can't be 1, right? So as long as x is not 1, and I can even just like make a picture of this whole thing, right? When I plug in to this function, when I plug in 1, I get 3. Boom. When I plug in 0, I get 1. There's a vertex at negative a half comma 3/4. And it's like symmetric because it's like a parabola and stuff. So this is a basically accurate graph of the g function, except for one thing I need to fix.
Hole at 1.
There is a hole at x equals 1 because this function is actually undefined at 1. And now it becomes clear, this is now visual, this is algebra, also visual, that what is happening to this g function as x gets really, really close to 1, the output of the function is really, really close to 3. All right, are we good? Good. Okay, back to the worksheet for more working.
Do we proceed to work?
Number 2, I think is good.
What is?
Where the circle was, I did. I mean, number 4. Number 3. I still have
I can tell you're reading. I missed like one sheet and I saw the letters.
honestly,
They are, man. Yeah,
like it has like too strong of a taste.
Carlos, that's like basically just pasta.
Croutons are just like, maybe if you buy croutons, they're like over 60. We generally
I hope that shows up on the video.
it's us talking about
That would be kind of hilarious.
No, but he's gonna edit out just like regular words. I know.
No, he doesn't.
He does. He leaves it in so that you can like do it and just like leave it going.
Yeah.
I don't
Oh no. Salad down. That's next to the salad.
Alright, I'll put it in the hospital.
Okay, let's keep on 4.
How do you do 7?
7, it just like it's straight up just different squares. And over 7 is just different squares. You get
same thing as
cross
one
multiplying, it's not actually cross multiplying, I don't know what you call it, cross multiplying. And then
You're cross.
that was the worst noise ever. Why is that even funny?
Alright.
What? Yeah, different to squares, but with like a square root. Just different to squares to square root.
Multiply
Bye, camera.
x plus what? I don't see how that
Is on
Wait,
A little bit by 3.
somewhere has to be discussed.
Yeah, if you just fasten it down, it just gets That's unfortunate.
Alright, how about number 2? Seems like people are more successful with that. Talk to me, what'd you do? Woo, Ethan.
Start out with you make like a trig entity to make that 2 sin x cosine x.
Okay, he says apply a trig identity, but why? I didn't want to do that just for fun. I want to do it for like a reason.
Because it's easier to. It's easier to. Oh, actually, that wouldn't be easier because it's already 0.
Okay, wait, good. Pause on you. Someone else. What should we do? Yeah, Priya.
Sine of x is about equal to x once the value gets really, really small. So you can just say 5 times 2x over x, and then you can try to find the limit of 5 times 2x over x, and then canceling with x just becomes the limit as x approaches 0 of 10, which is just 10.
Okay, wait, hold on. She solved my whole problem for me, but I wasn't even convinced that there was a problem yet. What's like the first thing that you should just do? Just like first, yeah.
Plug in x as 0.
Yeah, just let's like, that's like important psychological moment, right? To just say, okay, if I want to know what the limit is as x approaches 0, then all I want to do is know what happens near 0. So let me just try to very casually just plug in 0, and maybe the answer will just be immediately clear. What happens if I plug 0 in the top?
5. Wait, no, 0.
0. Yeah. Yeah, because if I plug in a very, very, very tiny number, times 2 is still very, very tiny. Sine is something very, very tiny. Is tiny. Times 5 is still tiny. Yeah? Everyone with me? Okay. And the bottom, of course, is going to 0. Okay, so you need to like actually do that step. And then what should we like sort of say to ourselves when we see that they're both going to 0? This is like a 0. This is a 0 over 0 situation. And then you have to sort of say, oh, when I have a 0 over 0 situation, I do not know the answer. And since I don't know the answer, that means I have to actually like do something. And okay, now let's return to the like what to do. Wait, which of you was it? Was it you? No. It was before Priya. It was someone else.
Talk about trig identities?
Yeah, is that you? Okay, yeah, good. So Ethan says, let's apply a trig identity. That is one way to do this problem. Sine 2x, 2 sine x, cosine x. And so this is just like 5 times 2 sine x cosine x over x. And then he said some other things. Actually, I sort of stopped listening to him a little bit. But I think what he said is something like, well, what's happening as x goes to 0 of cosine? What happens to cosine very, very near 0? It's pretty much going to 1. And what is happening to sine x over x as x is getting really close to 0? It's going to 1. All right, so this is going to 10, and this is going to 1, and this is going to 1. This is not obvious at all. But this is something that we learned last semester, and we spent a whole long time talking about it, yeah? And the rationale that we gave for this fact was a geometric rationale. We said, based on the very definition of the sine function, I'm just like reviewing this so everyone's got it. Based on the very definition of the sine function, if you give me some arc length in radians, that arc length is in fact the input to the sine function, and the height of this is sine x, and so sine x is always going to be a little bit less than x in the first quadrant, but when x gets, does everyone remember this conversation like it was yesterday? Yeah. As x gets really, really small, then the ratio between these two goes to 1, just because it just plausibly does. More on that later. And so the answer to this problem is indeed 10. Okay, everyone good on that? Did most people get this, like before we just went over it now? Yeah, good. Okay, Priya said something else. I didn't 100% follow her, but I think she said something like, I don't really need to do a trig identity, actually, right? What Priya said is, this is a sort of different approach, possibly better. She said, well, look, once you accept the fact that sine of something over something is very, very close to 1, then that something could just as well be 2x. So multiply the top and bottom by 2. And if you do that, you just get 10 times sine 2x over 2x.
That's clever.
That is clever. Is everyone seeing this?
Yeah.
Sine 2x over 2x is just going to go to 1, so this is just 10. All right, how are we doing? They're good. Okay, good. Let's do number 3. What is the limit as x approaches 2 of 1 minus root x minus 1 over x minus 2? What's the first thing we should do?
Plug in 2.
Yes, we should try to just plug in 2 and see if the problem just reveals itself immediately. But it does not, because what happens when I plug in 2?
0.
Yeah, exactly. Yeah, it's a 0. The top is basically 0 and the bottom is basically 0. So this is a 0 over 0 situation. And as we discussed, like we can't know what the answer is. So we have to do something. We have to do some algebra, some further analysis. Everyone cool? Okay, what is the further analysis here? Well, there's like this one algebra move that's not totally obvious, but is a very good move, which many of you, it seems like, figured it out. Well, Aga, what do we do?
Split the bottom into x minus 1.
Oh, that's like a weird thing. I see what you're doing. That's like an even more obscure way of doing this. Yeah, okay, so like, it's kind of like this, right? This root x minus 1, like what is like root x minus 1 like even mean? What is like the square root of a? Like what's the definition of square root of a?
Something that we're like square root of a times the square root of a equals a.
Yeah, the square root of a is the number which when squared is a. Well, so x minus 1 is like the number which, when squared, is x minus 1. Do you see how like the very definition of the square root is like referring to some future action that you might take? It's like if you have a genie which, when released from the lamp, will grant you 3 wishes. Then what's the thing you should do with this genie? This is stupid. You should let them out of the lamp, right? Good. It's like I somehow can't get to this information. The information of root x minus 1 can't be used until I like do the squaring, because it is the thing which when squared is x minus 1. Follow? So somehow I need to like square this. but I can't just go squaring things just because I feel like it. So how can I make this square root like go away, so to speak?
No, don't square both sides, that's bad.
There is no sides. There are no sides. It's just an expression. Wait, I saw a bunch of you do it right on your papers.
Multiply the top and the bottom by one.
What's why the conjugate?
Yes, there is a well-known algebra move called. Yeah, your way is slightly better, but it's like too creative. Yes, that is indeed the conjugate of 1 minus x minus 1 is 1 plus x minus 1. Alright, this assumes that you have some experience with multiplying by the conjugate, and like you just do have experience with this from like, I don't know, when have you done this before? Like if you give me 2 over like 5 minus root 3 or something, and someone says like do something with that, right?
Yeah.
Then that's what you do. And this is like a good system because the bottom is now difference of squares, and so like things happen. Is everyone, can you like nod along and feel like yeah, we're with you? Woo! Good. So that's 25 minutes, is like 22 on the bottom, and 2 times 5 plus root 3 on the top. And whether this is actually like any better than the way it was to begin with is like a matter of taste. But anyway, that's certainly a thing that you have done before, yeah? Okay, so finish this problem now, go. Gotta work on that. Yeah. Yeah.
Oh, come on.
Yeah, that was like a trick or something. Are you guys like done?
Come on, dude, the creative mode is cool.
It's like 2.
What's up?
The creative mode is cool. I did a creative mode, and I also did it on top of it.
Yeah, you're trying to do this thing where you're trying to like break down these apps.
Do you like a square and then
All right.
it's 0 over something?
0 over dog.
Yeah, no, I haven't had
That's so
No, wait, isn't 2 minus x just
except that
Wait a minute.
because we have like
Alright, are we all doing the same extremely careful algebra and getting it all right and stuff?
Wait a minute, that's 54 negative 1. This is
Right? Yeah. Okay, good.
and then we
So,
have Chad and
what happens is we get cancellation, y'all. Is everyone, am I going too fast or too slow? Or just right? Alright. So this whole thing turns into the limit as x approaches 2 of -1 over 1 plus root x minus 1. And now I should once again just casually try to plug in 2. It's no longer indeterminate. If I plug in 2 now, what do I get? -1/2, because this 2 minus 1 is just 1, the square root of 1 is just 1, so this is -1/2. So the moral of the story is like that answer, -1/2, is not something you could have like predicted. So there's a certain amount of like, you just have to do the algebra to get the right answer, yeah? Okay, good, yo. Oh, you can also do that, yeah. There's a couple other techniques which boil down to essentially the same thing. So yeah, there was the Annika method was to do something even more fancy, which was essentially the same as what you're saying, which is to recognize that x minus 2 is really like x minus 1 minus 1. And that this can be thought of as the difference of squares. This is what you guys did, right? So then this is 1 minus root x minus 1 over like root x minus 1 minus 1 times root x minus 1 plus 1. And then yeah, and then it's essentially the same thing. When instead of multiplying by the conjugate, you're sort of like extracting the conjugate, so to speak, from the difference of squares. But it's fundamentally, it's all about difference of squares. Maybe you like that better. Okay, keep going, keep working on this worksheet for like 2 more minutes, and then we're going to go over the whole thing.
Okay, so number 4 we have root x plus 6 plus 2. Okay, I know how to calculate about. I know how to do that.
We have 10 full minutes.
From here, we cannot plug into. Every time we have.
Wait, my area on the
Two over all of like a
Okay, let's get rid of these. X squared minus 9. So we have to denominate.
What's up?
John Michael. Chuck David.
Table like that.
Want to do number 6. What follows?
technically you don't even need the graphic.
Alright, number 6 is just what's the limit as x approaches pi plus of cosecant. There's a couple ways to do this. You could just, like me, just know the graph of cosecant, just kind of cold, and sketch it either on the paper or in your brain and just see that it's just doing this, yeah? And so the answer is? Negative infinity. Alternatively, you could do a unit circle based approach, and you could say, okay, here's the unit circle. If x is approaching pi plus, then I'm talking about an angle which is just like a little bit more than pi. And if this is a little bit more than pi, cosecant is by definition just like 1 over y, right? And so this is going to, right? So this is going to be 1 over whatever the y coordinate is of this point on the unit circle. But that y coordinate is going to be a very, very tiny negative number. And so this is 1 over 0 minus, so answer is negative 3. Number 2 is just a kind of easier version of number 1. Or sorry, number 5 I mean. What else is on here? Oh, should we do number 4?
Yes, that'll be good.
Number 4 is meant to sort of bamboozle the people who are just mindlessly doing algebra for no reason. Because it superficially appears to be just like number 3, but it's not, because the first thing you should try to do is just plug in 3 and just see what happens. And indeed, what does happen when I plug in 3? Yeah, the top is basically 2. So that's very comforting. And the bottom is basically 0. So already I am into the world of realizing that this is not a 0 over 0 situation. This is like an approximately 2 over approximately 0 situation, and therefore we're expecting like infinite behavior, because if you divide by something really tiny, you get something really huge. Yeah. Okay, but we have to be a little bit more careful, because it depends on, is this a tiny, if this is a tiny positive down here, then I'll have infinity. But if it's a tiny negative, then I'll have negative infinity. Which is it?
No.
Okay, good. I heard it doesn't matter. I heard it both, and I heard it depends. I think depends is the best answer, right? It depends on whether x is a little bit more than 3 or a little bit less than 3. So we should, if we're being careful, then just consider both cases. So if x is a little bit more than 3, then this is root x plus 6 minus 3. Okay, well now this numerator is still pretty much 2. And the denominator now is, well, a little bit more than 3 plus 6 is a little bit more than 9. Yeah, square root of a little bit more than 9. A little bit more than 3. Minus 3 is a tiny positive. Can everyone handle this like manipulations with tiny things and big things. So what is 2 divided by a tiny positive? This is going to infinity. Okay, so indeed this is going to infinity to the right of 3. But if we look at what happens as x approaches 3 minus, what do we learn? Well, the top is still 2. The bottom now, well, if x is a little bit less than 3, then x plus 6 is a little bit less than 9. Yeah, thank you. Crap. And if I take the square root of a little bit less than 9, then a little bit less than 3 minus 3 is a tiny negative. And 2 over a tiny negative is a huge negative. Cool? Okay, so what we're expecting this thing to do is on one side of 3 go up to infinity, on the other side of 3 going down to negative infinity. This is not so crazy. This is the kind of thing we saw with rational functions. And therefore we just say that the limit as x approaches 3 of x minus 1 over root x plus 6 minus 3 just does not exist. Okay, good. There's like 2 more, 7 and 8. Are they like pretty chill?
Yeah.
Someone with good handwriting, go here. Can you put these up on the board? I'll be back in 1 second with some more problems.
Which way should I move it? Okay, I'm gonna move it. Dave, say no.
Specifically, it's 0 plus. I mean, no, it approaches 0 from the top.
I'm gonna move. I want to move it over there. How does he move it? Does he just pick it up? Okay. I know, but like.
That's why I spent 3 years at Eastern studying this. Like,
When Mr. Patel talking about Jacob already responded with in notes. Hey, thanks, Aaron.
yeah, and you can flip the screen. Check Aaron. You can also flip it upside down and it'll like auto.
I'm actually just gonna keep it on.
I know.
This is auto rotate.
Yeah, that's just like right? I think it does. Yeah, it auto rotates.
Whoa.
Not after.
Yeah, I know. Those are obnoxious.
No, that's just like no. Wait, are you talking?
That's funny, dude. It's like he's.
Yeah, and they got like.
Jesus, literally the same thing. Behavior of the
Like, I agree. And I like the concept of ads.
So if you factor it in, plug it in.
I just thought it was the same thing. I always say
Except when they get 0 minus.
oh yeah.
9 times
No, it
0
says don't
over negative 3 times.
Oh yeah, it says don't.
How
did you get 9?
So that's 0
numbering again, it appears hard, but if you just plug in 0, if you just plug in 4, on the top you just get 0, and on the bottom you just don't. So the answer is just 0. But if you overthought it, you could have factored it, which this person did, and they even made a graph and stuff. That might be right. And